What if I told you you could walk through walls? You probably wouldn't believe me, and for good reason. Our natural understanding of the world just doesn't permit weird occurrences like these. But does that mean they don't exist? Enter quantum physics, a field that describes small particles like electrons and photons with some unexpected results. Let's sidetrack a bit. Suppose Schrödinger, yes, the Schrödinger, goes out and buys a cat after the last one died. He puts the cat inside his house, goes out to do some errands, and comes back an hour later. Where would the cat be? True, there's an equal probability that the cat could be anywhere inside the house, but here's the catch. Before he left, Schrödinger installed a cat door in the front door, so in fact there would be a small chance that the cat left the house. Of course, there would be a smaller probability that the cat would wander outside than stay inside, but the probability is still there. Now back to quantum physics. Replace the cat with a particle and the door with any barrier. Quantum physics says that there's a large probability that the particle will remain on the left side of the barrier, and a very small possibility that it will appear on the right. But unlike the cat, which has to physically cross through the door via a cat door, the particle doesn't have to cross through the barrier at all. It just appears on the other side. This is known as quantum tunneling, and it's one of the most intriguing topics in quantum physics. Because we're dealing with particles, we can use an actual equation to calculate the probability of finding the particle anywhere in the house, which we'll call the x-axis. Let's put the barrier at the position 0. Luckily, Schrödinger published an equation in 1926 that can be used to describe the quantum state of a physical system, aptly named Schrödinger's equation. It looks really confusing, so let's break it down. Schrödinger's equation relates a particle's mass to its energy, the surrounding potential energy, and the probability of finding the particle at a particular x position. We're interested in the last part, the probability of it being at a particular x position, which is called the wave function. Remember, a function is some map that takes a value, in this case x, and returns another value, in this case the probability. But there's a problem. In Schrödinger's equation, we can't simply solve for the wave function since there seems to be some sort of funky operator here. This is called a partial derivative, and it scrambles the wave function in a particular way. We need to unscramble it to get back to the original wave function, but this requires some advanced calculus way beyond the scope of this video, so we'll just skip to the final answer. It turns out the wave function equals a times e to the minus square root 2m v minus e over h squared, all times x. V represents the particle's potential energy. To the left of the barrier, the particle doesn't experience any potential energy because nothing is compelling it to move a certain way, so V is 0. The particle only has its own energy moving it around, E. H is Planck's constant, a number that's often used in quantum physics, so we'll substitute it in, and we'll replace m with an arbitrary mass. For our purposes, we can eliminate this coefficient a, which is pretty much random. Since we're dealing with the left side of the barrier, all the possible x values are negative, which cancels out the negative sign. Since the particle's energy E is positive, V minus E will give us a negative number, which surprisingly creates an imaginary number in the exponent because of the negative under the square root. You might be thinking to yourself, what would this function look like on a graph? It turns out the function resembles a wave, sort of like a sine curve. But hang on, since the function dips into negative values, does that mean that there's a negative probability of the particle existing at certain x values? Actually, to compute the probability, it turns out we have to take the absolute value of the wave function and square it. And as you can see, the function flattens out, so the probability of finding the particle anywhere to the left of the barrier is equal. This is exactly what we saw with Schrödinger's cat when we noticed that there would be an equal likelihood of Schrödinger finding the cat anywhere inside his house. But now for the interesting stuff, what is the probability of finding the particle inside the barrier? You would probably answer 0, and that's what makes intuitive sense. But what about the physics? The barrier actually creates a potential energy that prevents the particle from crossing. In the cat scenario, if the cat door were too high, the cat wouldn't possess enough energy to jump through the door and land outside. Similarly, we can imagine a barrier that imposes a potential energy on the particle that exceeds the particle's own energy. Would this prevent the particle from crossing? Actually, no. In this case, V minus E would be positive, and we wouldn't get an imaginary number, so the wave function would be e to the minus x times some positive number. In fact, this is the exponential decay function. So it turns out that the probability of finding the cat inside the barrier drops really quickly, but it's not 0. On the right side of the barrier stops exerting a potential energy on the particle, so V minus E becomes negative, and once again, we have an imaginary number in the exponent. We find another sine-looking curve on the right side, but because of the enormous drop in the probability due to the exponential decay, the amplitude or height of the curve on the right side is much smaller than that on the left. After squaring the absolute value of the function, we we find that there's an extremely small probability of finding the particle on the right side of the barrier, but the probability is still there. This is similar to the cat scenario, where the cat had a small chance of being outside the house. To me, this is one of the most astounding consequences of quantum physics. The fact that particles with little energy can literally tunnel through barriers is amazing, and it goes against everything we see in the real world. But in fact, quantum tunneling happens every single day, in a place we all know of, the Sun. In the Sun, a process called nuclear fusion joins or fuses hydrogen atoms together to form helium, releasing huge amounts of energy in the process. Much of this solar energy sustains Earth. However, for nuclear fusion to occur, the hydrogen atoms must be really hot. The Sun's internal temperature is only about 15 million kelvins, which isn't enough energy to overcome the barrier of repulsion between the hydrogen atoms, which are essentially protons. Remember what we said about quantum tunneling though? There is a very, very small chance that the particles can overcome the barrier through quantum tunneling. But since the Sun has tons of hydrogen, these small chances add up, and nuclear fusion happens all the time. Back to the original question which prompted this entire video. Would quantum tunneling let people walk through walls? Unfortunately, no. As the mass of the object increases, the exponential decay function inside the barrier compresses rapidly, so the probability of the particle appearing on the other side is practically zero. This partly shows why many quantum phenomena are restricted to small particles like electrons and photons. So the next time you have to cross a wall, you might be better off digging an actual tunnel.